All right. So remember that PAB equals to determine Q KAB minus QAB. Okay, so P is determined by Q and K. K is the extrinsic curvature. So which means we only need to take care of K. And so well, K and Q determine P. Okay, so now we can write KAB to be KAI IB. Okay, so which means that the second tensor slot, for the second tensor slot, I expand using the basis, using the orthonormal basis, right? All right. So by the way, so here we get orthonormal dual basis. Then of course it uniquely determines the basis EAI, which is orthonormal basis, which is the inverse of EJK, and this is the orthonormal basis, and called the triad. So, and once we have a dual basis, of course, it uniquely determines a basis, as we learned before. Okay, so now what we want to do is, for example, we can use KAI and EIA as dynamical variables. Well, this is at this moment it's just an idea, yeah, from motivated by these two formulas. Yeah, but finally it's not exactly like that. But finally it's not exactly KAI and EIA are dynamical variables. They are interested, but the idea is this. Okay, so then suppose we can use this as the dynamical variables, and then this KAI, EIA, of course, uniquely determines QAB and KB, and then this variable uniquely determines QAB and PAB. Yeah, and then we recover the ADM variables. ADM variable. Yeah. However, although from left it can determine the right, but from the right it cannot uniquely determine the left, and there are gate redundancies. But we introduce some more gate redundancies by these variables. They are additional gate redundancies. Additional gate redundancy. So what is gauge redundancy? So we can make a linear combination of these E's, make a linear transformation of these E's, EAI transforms to OIJ. OIJ is the matrix, EJA. Okay, and correspondingly, so here it's like we are transforming this IJ index, and KAI transforms into KAI O inverse IJ. Okay, and this matrix O is a 3 by 3 matrix because IJ both runs from 1 to 3, but this O belongs to so-called SO3 group. Yeah, so what is SO3 group? They are group of also orthogonal transformations. Yeah, so or it's called special rotations, special orthogonal transformations. Special means determinant equals to 1. Special rotation. Special rotations of basis. basis. So what I mean by special rotation basis, it means that so O ij O k l delta ik equals to delta jl. Okay, and also this s means that determinant of O equals to 1. Yeah, so here this formula tells us that the determinant of O can be plus or minus 1, but special rotation means that determinant O equals to 1. So it's fixed one sector of the gauge transformations. Okay. All right. So now you can see that we introduced some additional gauge redundancy, and well, actually, I don't really need to make this fix. It can be just O3, not SO3. But yeah, to be more specific, because it will be useful later on. Then let's fix from the beginning that the determinant O equals to 1. So here, just apply this formula. Yeah, you can see that this gauge transformation applied to this formula applies to these two formulas. It gives the same Q and K. Yeah, so this kind of transformation of E and K, it gives the same QAB and KAB. So that's why we say that there are some additional gauge redundancy. So in this new variable K and E, there are some additional gauge transformation which changes K and E, but leave Q and P, leave ADM variables invariant. Yeah. Okay, that's why we say that we enlarge the phase space, because we include some more degree of freedom, some more gauge degree of freedom. So once, I mean, from we learned before, once we have a gauge transformation, we definitely have a constraint. Because in canonical formulation, gauge transformation corresponds to a constraint. Then here, there is a constraint. Okay, what is the constraint? So from K and E, you automatically get a constraint is here. So KAI. Okay, so we can consider EAJ. Yeah, so we KAI with KAI EAJ. So KAI is like the second slot of KAB. I replaced two components, but now I contract with the triad, the basis EAI. What we got is KJI. Yeah, we got KJI, which means we also get components of the first slot. Yeah, and remember KJI is just a component of KAB, and KAB is a symmetric tensor, so which means that KJI is also a symmetric matrix. It's a symmetric matrix. So it means that KJI anti-symmetrization equals to 0. It means that KAI, so it's equivalent to say that KAI EAJ IJ anti-symmetrization equals to 0. Okay, so this is the constraint. Yeah, so you get K is a symmetric tensor, so you get automatically this constraint. So KAI EAJ anti-symmetrization with IMJ equals to 0. So there's a constraint. And then, well, it's a matter of check that this constraint really generates this gauge transformation by using certain Poisson bracket, but right now I haven't tell you what is Poisson bracket yet. So okay, but the scheme, the idea is that we get this gauge transformation. We also have this constraint. So they are the constraint and gauge transformation. They are one-to-one correspond to each other, and you can even count the numbers of gauge transformations. So you have special rotations. So you have 3 gauge transformations. SO3 is of dimension 3. You have rotation in x-axis, y-axis, and z-axis. You have 3. It's generated by 3 different kinds of rotations. So dimension is 3. And so here you can also see you also have 3 constraints. three constraints because ij is undisymmetrized. Both I and j runs from 1, 2, and 3. Okay, so the number of constraints indeed matches the number of gauge transformations. Okay, so now we can also counting the degree of freedom to see all the story is consistent. Counting degree of freedoms. So the original, we start with the variable ei, a, and kai. So it has so eai is a 3x3 matrix with no symmetry. Yeah, so you have 9 degree of freedom, 3 times 3 is 9, and kai is the same. It's a 3x3 matrix. It's 9 plus 9. This total number of let me say not degree of freedom. So before we say degree of freedom is half of the phase space. Counting dimension. Counting dimension of phase space. Yeah, so it's 9 plus 9, of course, times infinity. So at every point. And now you have 3 gauge transformation per point. Gauge transformation. And so let me be more precise, times infinity. And you have 3, so here it is 3 times infinity gauge transformations. And you have 3 times infinity, 3 times infinity constraints. Okay, so in total you remove 6 times infinity. So, or it's like you 3 times infinity removed from E, 3 times infinity removed from K. Then the result is exactly QAB and PAB. Yeah, which is 6 plus 6 times infinity. Okay, and the dimension indeed matches because 9 minus 3 is 6. All right, so before we finish, I'd better tell you the Poisson bracket here. So here, the extra canonical variable which is used here is this. So let's say consider the canonical variable. Canonical variable. This. So firstly, we define something called densitized triad, EAI. So I put from now on the density. I don't want to put a twiddle on because that's complicated. I don't want put twiddle on densities. This is called the densitized triad. Densitized triad, and the conjugate variable is kia. Well, it's just the kai. Raise up the index is free for this I because you raise up using delta. So you can raise and lowering ij index without care. So well, what we call is this is just called extrinsic curvature, although these are somehow the components of the extrinsic curvature. And those variables they are not Ashka variable. They are intermediate steps of toward Ashka new variables. And these are called triad ADM variables. Triad ADM formulation. So these are still similar to ADM formulation, but here we just use the triad ADM formulations. Yeah. So now the phase space. Now this is the phase space. Phase space, and well, this is it's not the reduced phase space, but the phase space at before taking account constraints. Yeah. So the coordinates are KAI and PAI, KAI and EAI. Okay, And the Poisson bracket is defined as the following: f and f prime Poisson bracket equals to kappa divided by 2. So here you see when I put the kappa in, so I have to kappa divided by 2. So this is the trick to make this Poisson bracket equivalent to the ADM Poisson bracket. So here I and AA are summed, just like X is integrated. Here D3X. This is integrated over sigma. Okay, so by plug in K and E for this Poisson bracket, you can easily see that. So it's EI, EAI, X, K, E, J, Y. Okay. Y equals to kappa divided by 2 delta Ji delta AB, three-dimensional delta function. Okay, and as the other Poisson bracket EE Poisson bracket equals to KK Poisson bracket equals to 0. All right. Oh, okay. This is too late now. Right before that, right before we finish, I think I just write down 2 more formulas and explicitly show you how E and K, this variable relates to ADM variable. So, okay, so QAB equals to, to relate ADM variables, EJA, EJB, JB, and then the absolute value of determinant E. E is again the 3 by 3 matrix. Yeah? And so here EJA is just the inverse of EAJ. Okay, this is Q, and PAB equals to 2 times determinant E inverse Okay, so repeating index. So here JJ means the sum, no matter up or down, because for IJK index, you are free to move up and down. BC.
Now you P or P Twitter?
I'm sorry?
You P or P Twitter?
What?
You P the more you density or your tensor density P should be here.
Okay, so as I said, I don't want to put the twiddle on anymore.
Oh, okay.
Well, I'm yeah, if you like, I can put it on. So and for density, because all the time it's annoying to all the time put the twiddle.
Okay.
Okay, so then the phase space is really equivalent to the well, at least the Poisson bracket. Of course, you get more dimension in the phase space compared to ADM. But the Poisson bracket is really equivalent. It means that from these Poisson bracket for E and K, you should be able to derive the Poisson bracket of ADM. So then indeed, so from this formula, you just plug in Q and P to this tried ADM Poisson bracket, to this Poisson bracket. You plug in this P and Q. Yeah, so what you can check is that PAB X Q C D Y kappa equals to kappa delta AC delta BT delta 3 X and Y. Well, yeah, okay. It's fine. So here, here it's just I'm using abstract index A, B, and C, D. So here, right-hand side is also abstract index A, B, and C, D. But you can also understand the same formula using concrete components index. So here, well, this will allow you to the twiddle. Then you can, it's really straightforward to derive this formula from upstairs. But here you can see that actually this Poisson bracket is different from the previous one up to a minus sign. Before, when we talk about ADM, the Poisson bracket is QAB, Q in front of P. So Q Poisson bracket is P equals to kappa delta. But now here is P in front of Q equals kappa delta. So there's a minus sign. It's something, it is exactly something what I mentioned before. I'm now changing actually for some future convenience, I'm changing my convention from kappa to, which means I put the overall minus sign in front of the action. So this is something I discussed last time already. So I can sometimes change the convention. So indeed, when I'm talking about new variables, I'm going to change my convention so that the Poisson bracket now is P in front of Q equals to kappa times delta function. Okay. So here, these I'm going to leave you as homework to check this. But now I'm giving a reference for you in case you stuck somewhere. The reference is Tieman's book. Tieman's book. The name is called Modern Canonical Quantum Generativity. Modern canonical quantum generativity. Okay, and this book will be our important reference. So I have also listed this reference to the lecture webpage. Yeah. Okay, so on this book you can find some details about this derivation, but this is your homework to try it by yourself. All right, so I think that's all for today. So if there's any questions, whether you have any questions, it's probably a good time to ask.
Yeah,
okay.
If there's no other questions.
All right. Okay. So if there's
Professor.
No, sorry, you have a question?
If there's no other questions, can you? I missed the first 5 minutes of the class. If I could just do a screenshot of the first part of the notes, is that okay?
Oh, sure. Well, the entire note will be online, right? I mean, you can find it as well.
Okay.
Yeah. So you can find the. So I have sent around the email, I guess. Did you receive my email about the web page?
No. No, I didn't. But can I? I'll just email you if you could just.
Yeah.
Okay.
Sure. Yeah.
Oh, okay, I appreciate it, Ian.
Yeah, there's a web page for this lecture, and then on this web page there's a link for the note for all the lecture notes. Yeah, and also all the lectures will be on YouTube. So I have uploaded all the previous lectures on YouTube.
Oh wow. Okay.
Yeah,
that's awesome.
Starting from ADM formulation, I upload all the videos on YouTube, and also below the YouTube videos, you can also find the links to the lecture webpage and notes and lecture notes. You can find links as well.
Oh, great.
Yeah.
Great.
And well, all the previous lecture videos on generativity has been on the Canvas, has been uploaded to Canvas. Probably that you know, right?
Okay. All right. I appreciate it. Thank you.
Okay.
I have a question about smeared constraint. Why do we need to use this kind of objects? I mean,
Okay, very good. So why do we need a smear constraint?
yeah,
So smear constraint, it's okay. So this is a smear constraint, and well, as I said before, when you smear the constraint, it is manifestly a functional on the phase space. It's a functional of P and Q, so it's a function on phase space, right? And the good thing about it is that you can write this formula in a much simpler way. Now you can write this formula in a compact manner. And suppose, of course, you can use just the unsmeared constraint. It's fine because if you fix x, it's still a function on the phase space. It's definitely fine. You can do computation with it. But the thing is that you will get more complicated formula in this on the right hand side. A little bit more, it's not very much more. On the right hand side, it's less compact, at least less compact as this formula. This first disadvantage. Second disadvantage is that it's very distributional. You have to manipulating those distributions. So because Poisson bracket between P and Q give you delta functions. Delta function is a distribution, and then you also, because the formula of constraint has derivative act on P and Q, so which means in the end you will have derivatives act on delta functions, right? So you will get some distributional quantity on the right hand side, which is clearly fine if you're familiar with distributions, but it's less, as I said, it's less compact and it's not as clear as a just ordinary functions, Lie derivative, and so on.
okay, so it's for convenience.
Yeah, it's just for convenience. Yes.
Okay, thanks.
So I have a question.
Okay.
So when you were saying that the actual constraint to fix the phase transformation, the O matrix. Yeah.
Yeah, here it is. Right.
The three constraints. Yes, there is a constraint that there. Can you scroll down a little bit?
Okay, so this is, you mean this constraint are corresponding to this SO3 rotation.
Yeah. And this anti-commutation relations equals to 0 is normally the one that you said that cotetrad this is the triad. So this is what you mean by triad is compatible with one form connection, right?
No. It's here. Do nothing about connection. No. Definitely no. So here you have no connection yet. So here you here this K is just extrinsic curvature. You do nothing about connection. Why you relate to connection?
Because K is
the extrinsic curvature. So these constraints come from K being a symmetric tensor. So they do nothing about connection and or compatibility of E with connection.
But we can express this this K with that one form spin connection, right? In the
one form spin connection. No, it's completely independent. K is completely independent of spin connection. Spin connection relates to the spatial metric. K is something else. K is independent of the metric. K is extrinsic curvature.
Okay.
No, so it's here it do nothing about connection. So here I haven't even introduced connection. So here you get this constraint just because K is a anti-symmetric. K is a symmetric tensor. So the anti-symmetrization of the symmetric tensor is 0. That's this constraint.
All right.
Okay. So any other question?
Maybe before doing the process, we need to prove that K is a conjugate momentum over E, right?
Say again. Can you say again?
Before doing this
We do this process. We need to prove that K is the conjugate momentum of E, right?
We need to prove K is a conjugate momentum for E. So here it is. So here it is what I'm claiming is the conjugate variable. So E and K, right? So this is not more E and K is they are not exactly conjugate. They are roughly conjugate, but not exactly conjugate. But this is this capital E, which is a densitized triad, and the KAI. They are real conjugate variable. So,
Okay.
yeah, and then this is exactly something I want you to check. So when I define K and E to be conjugate variable, so define this Poisson bracket in the phase space K and E. So you are going to check that you can derive Q and P. They are conjugate variable. It means that, yeah, so the ADM phase space can derive from this new phase space.
Oh, okay.
Yeah, I think that's what you mean by equivalent.
Yeah.
Mm-hmm. Okay, so any other question? Okay, if there's no any question, then we should stop.
Okay. Thank you.
Okay, thank you.